Okay, so we're going to finish off chapter 3 today. On Tuesday, we'll review for your first test, and next Thursday will be your first test on chapters 1 through 3. The review test is done. I forgot it at home, but it'll be posted on my website after this class. So you can just download it. It'll be a PDF file. You can download it, throw it on your phone or whatever else to be able to see it. We will do the actual questions in class on Tuesday. So go through, attempt it, try it, use it to make your index cards or start your index cards. So if there's something on the test that you don't remember how to do, make an index, put it on your index card. So this way you can use it on the actual test. If there's specific questions and stuff like that, on Tuesday, we'll answer them. So you can go through and do them. But definitely try it before you come to class on Tuesday. So this way you can get your mistakes fixed before Thursday. Okay? It will cover everything. It's not every single exact thing that we covered because obviously there's not enough time to do it all. But it'll hit the main points and stuff like that, the things that you're going to need going forward, which is really the goal of this test. Because after this test, we start to get into new stuff that you probably haven't seen or done before. So, all right. So the last class, we ended up talking about different ways to find central tendency. We looked at mean, mode, median. We were finding average of things, stuff like that. And then we started looking at the very end, we did standard deviation. We were looking at figuring out variance and how spread things are. Today, we're going to start looking at how we actually use that to determine some information and how we can display the variance and how things are spread. So here's 3 different graphs. We've got a skewed to the right, skewed to the left, and then the normal bell curve there. When we're looking at standard deviation, one of the things, well, actually, glasses. If you were going to look at the graph, what are some of the things that you'd want to know or want to be able to figure out from this? If you know the median, so the median's in the middle. So the median and mean in this case is right there. In this one, the mean or the median is there, but then my mean is pulled over. So that's the, and the same thing in this one. And my mean would be pulled this way. What are some information that you might want to know? Or what are some things that you might want to pull off this graph or be able to say, this is something that I know from looking at this picture? Yeah.
Well, say for instance, there's a graph on the right that says positive skew.
Yeah.
The positive skewed graph indicates that the mean is greater than the median, whereas the one for the negative skew, it's the opposite.
Okay.
The opposite for the mean and median, in terms of which value is greater than the other.
Okay.
And which one's less than the other. You know what I mean?
Mm-hmm.
Okay.
What are some other things you might want to know? What would be the purpose of showing a picture like this? Because remember, a picture's worth 1,000 words, right? There's actually meaning behind that. It's not just a nice saying that people say. It's like when you see a picture, everybody gets different things from it. So, what are some other things that you might want to show or get from a graph like this? Yeah.
The subject of the graph.
Okay.
What are they showing us?
Okay. Anything else? What about where the data is? Where's the majority of it? That's something you might want to know. Does it change based on the way the graphs are? Where the majority of the information is?
Yes.
Yeah, the skewed graphs, the majority is skewed, right? Opposite of the way that it actually says it's skewed. And the one on the bottom, the majority of the data is right in the middle. Another thing you might want to know is where you are on the graph. Anybody in here have kids? This is a different question that I normally, when I ask this question at night, totally changes the conversation. Anybody remember when you were a kid? If you went in the so if you're in school and I said you're an A student, so you're a 95% an A student, would that be a good thing or a bad thing? Good. Okay. If you go to your doctor's office and they tell you you're in the 95th percentile for weight, is that a good thing or a bad thing? A bad thing. Okay. However, this is where this conversation would change. If you have a kid and you bring your baby into the doctor's office, and the doctor says your child's in the 95th percentile in weight, and 95th percentile in height, the parents can think that's a good thing, because 95th percentile, 95, that's good, that's high. Okay, but that means you're way over here. Okay, and in terms of weight, that would be you're heavy. So you really want to be in the 50th percentile. But in the way our minds thinks about it, 50th is not good. 50 is average. For grades, 50 is bad. Yeah.
Wouldn't it be normal since like a child to be like a 95th percentile, since like when you're a baby, like you're pretty much heavy.
Right, but that means they're heavier than 95% of all the babies that have been tested. So that means they're heavier than you would assume to want. So yes, most babies' tendency to be a little heavier because breast milk and stuff like that tends to build on weight, but that's taken into account in the average already. So you really truly want to be at that 50, because that means you are average. You're right where you're supposed to be. Okay, but that concept changes your view. Okay, we think that's good when it might not necessarily be good. You want, as horrible as it sounds, you want to be average. You should be average. That's where the majority of people are. Okay, if I went through and I asked, okay, if you were to guess what your IQ was, what's your IQ? Almost everybody by essence would say they're way over here. Okay? If I was going to ask, you probably wouldn't say, yeah, I'm probably about a 90 or 100 IQ. You're going to say, yeah, probably 110, 120 IQ. Some, if you really want to think like really highly of yourself, 130, 140. Einstein was 160. Okay? Average is 100. So that's actually basically, this graph is a bell curve, shows the your IQs, 100 would be in the middle, and it's about a 10 jump between standard deviations. So you start to look at that, it's like, but most people don't want to be considered average. But that's where you should be. Now, you don't want to be below average. But the same reason why you wouldn't really want to be above it. You want to be right in the middle. So when you're looking at a graph, and we're going to start looking at what standard deviation does and what it means, those are some of the things that we're going to start to look at. You're going to start to realize how much data is really spread in there. How much information really is the middle. Actually, this graph is average heights of males. Is that 69? So it's like that's the spread that we want to look at. There's two main rules that allow us to determine this spread. So the two things you're going to always need for this is your mean and your standard deviation. Okay. Mean, simple. Standard deviation we get from the computer or the calculator. The first rule we're going to look at is the Russians. Chebyshev's rule. So, and the second rule we're going to look at is called the empirical rule. But Chebyshev's rule we cover because it actually looks at all types of data. We don't need a bell curve for this to work. Right? The empirical rule, we need it as a bell curve. And the vast majority of stuff that we're going to look going forward is going to be the empirical rule of bell curves, because we've learned how to make data basically fit a normal curve. But Chebyshev's rule allows us to look at it in terms of any type. So those skews where we have negative skewed and positive skewed, or left skewed, right skewed, those also can be looked at with this, but they won't be able to be looked at with the empirical rule because it kind of skews it. It pulls it one way or the other. What Chebyshev's rule says is that the amount of observations that lie within so many standard deviations will be equal to 1 minus 1 divided by k squared. So what this basically tells us is how much of the data is within that many standard deviations of the mean. Okay, so how much of the data is around that point. So when we look at this curve here, how much of the data is between here and here? How much information's in there? How many of the data points are in there? Okay. How much of the population would be in there? So this problem says forearm length. So if you look at the length of an arm, like one of the things that Leonardo da Vinci gave us was the Vesuvian Man. It was at all the proportions. Okay. Now, we have a skewed sense of beauty in this world sometimes, but the human eye and the human body looks for symmetry. So the closer you are to symmetric in your body, in your face, and everything else, the more beautiful you are to the human mind. Okay, it doesn't matter, colors and all this other stuff just clouds it, but it's actually symmetry that truly matters. And when we look at nature, that's what we see in nature. We see symmetry. So this helps with that. The closer you are to the mean, the more perfect you are, because that means you're perfectly symmetrical in that respect. So they sampled 140 men. The mean was 18.8 inches for the forearm length, with a standard deviation of 1.12 inches. So we want to know how much data is within 2 standard deviations. So let's start looking at what that means, because the first thing, before we even figure out like the percentage, let's see what that means. So when we're looking at standard deviation, I have 18.8 is in the middle. That's my mean. And my standard deviation was what, 1.12? And my standard deviation was, actually, we'll use S, these proper terms, 1.12 inches. So that means I can add 1.12 inches here. So from 18.8, I get 19.92. And I can subtract 1.12. And I get 17.68. So within 1 standard deviation, is the men's arms will be between 17.68 and 19.92. That's what 1 standard deviation means. Does that make sense? Yes? Okay. If we go out a second standard deviation, which is what this question was asking, we add the 1.12 again, and we subtract the 1.12 again. So if we add 1.12 again, we get 21.04. Somebody should be checking these because I'm doing these in my head and I'm bound to make little mistakes. 16.56. All right, so those are, now that's 2 standard deviations. So 2 SD is from 16.56 to 21.04. Now find me 3 standard deviations. So you're going to do it again. So 15.44 to 22.16. Just again, you're adding 1.12 and subtracting 1.12. Now, Chebyshev's rule states that it's the percent that's between those values is 1 minus 1 over k squared. This only works for more than 1 standard deviation because you can't do it for 1, otherwise it becomes 0. So if I was to plug in 2, what's 2 squared? 4. So what's 1 minus 1/4? It's a whole minus a quarter. Yeah, 3/4 or 75. So this is greater than 75%. So greater than 75% of all men should have between the 16.56 inches forearm to 21.04 inch forearm. It doesn't tell me the exact. It tells me it's greater than. Actually, technically greater than or equal to. Because it could equal 75%. Now, if we did 3 standard deviations, what's 3 squared? 9. So what's 1 minus 1/9? It'd be 8/9. Now, if you divide 8 by 9 in your calculator, you get 0.88888888. It keeps going. So we'll do 88.9%. So the nice thing about 9s is it's always repeating whatever number is on top. So 7/9 is 0.777777. 6/9 is 0.6666. Just whatever is on top of the 9s just keeps repeating itself. So within 3 standard deviations, we have almost 90% of all men would fall into that range. That's what standard deviation tells us. Okay. So if they had a forearm length of 23 inches, they're starting to get into that range of rarity. Okay. Because again, now think about it, the standard deviation was split in half, right? So half of my information should be down here and half should be up here, right? So if I'm way over here, more than 3 standard deviations bigger this way, what happens? We'll cut this in half. What do you get?
44.
Yeah, like 45. We'll round it off to 45. So if it's 45, I already have 50% over here, and another 45% on this side. If I'm at 23, I'm in the 95th percentile. Okay? That's what 95th percentile means. Is that you're more than 3 standard deviations. Like you're that far out. Okay? So, and that's actually with Chebyshev's rule. When we start looking at the empirical rule, you're going to notice it's even worse than that. Because Chebyshev's rule says it's greater than that but it could be way greater than that. And the only reason Chebyshev's rule doesn't give us an exact value is because it allows us to work with skewed data. It allows us to work with data that is multimodal, which has more than one peak. Okay. It allows us to have that spread because it allows us to work with any types of data. So, all right, does the concept of standard deviation, how it works, make sense?
Yes.
Okay, so do you understand that the mean is in the middle, right?
Yes.
So standard deviation just tells us how far on either side we're going to go. So that's where I added the plus 12, 112, and subtracted the 0.112. Okay,
18.8 or
that's the middle.
that's the mean, and then the 1.12 is the standard deviation.
Correct.
For arm lengths.
Yeah,
How
so
did you get the two standard deviations to be greater or equal to 75%?
that's Chebyshev's rule. So that says the Chebyshev's rule says it's 1 minus 1 over however many standard deviations I have squared. So if it's 2, k is 2. And that's what, so it's k squared is 2 squared, which is 4. So it's 1 minus 1/4, which is 75%.
I'm still kind of confused.
Do 1 minus 1/4 in your calculator.
Is it always gonna be greater than or equal to?
Yes, Chebyshev's rule says always greater than or equal to. And after today, we're going to very rarely use Chebyshev's rule,
All right, so I got it as 3/4,
which is 0.75.
75%.
Yes. Now, if you did 1 over, so 3 squared is 9, right?
3 squared is 9. Yep.
So if you do 1 minus 1/9,
Which was 8/9.
Right. and if you did 8 divided by 9, you get 0.88888, which is 88.9. That's what we did to get those percentages.
Okay, I see what you did there.
All right. So Chebyshev's rule works for everything. The empirical rule only works for when you have a bell curve. The empirical rule is what we're going to spend pretty much the entire rest of the semester using. All right, except for when we do probability, which is chapter 4. So Chebyshev's rule came around in the 1800s. The empirical rule came around a little bit after that. They're all actually based in calculus. So they look at the area underneath the actual curve. And in a calculus class, I actually teach them how to find this. What the empirical rule does is it works with a bell curve. So what we've found looking at massive amounts of data and stuff that we have over the past 100+ years is that once we get past, say, 30 to 50 samples, pretty much everything falls into a bell curve. Okay? And if we can make it work with a bell curve, we can make it work with this, which allows a lot of other calculations to happen. So the empirical rule, notice, doesn't really have a calculation to it. We're going to look at calculations a little bit later when we look at z-scores, but the general form of it is that one standard deviation is about 68%. So if we look back at my arm length that we just looked at a minute ago, we go back, between 17.68 and 19.92 is approximately 68% of all men would fall between them. That's what that empirical rule states. 2 standard deviations is 95%. Now, does that break Chebyshev's rule? What did Chebyshev's rule say for 2 standard deviations? Nope, that was 3. It's 75%. But it's a greater than that, right? Is 95 greater than 75?
Yes.
Yes. So it does not break Chebyshev's rule. So according to the empirical rule, 95% of all men are between 16.5 and 21.04.
Just a
Yeah.
quick question. Sorry for interrupting you.
That's right.
So for Chebyshev's rule, right? What does the K represent in that?
Number of standard deviations.
Number of standard deviations.
Yes. So right now that would be the 2, which was the 75%.
Yeah.
And the empirical rule now states that's 95%.
And then for the other one, what you got for 88 point,
That was 3. So K was 3.
K was 3, yeah.
Yes, that's how I got the 9, because 3 squared. The empirical rule states 3 standard deviations is 99.7%. So remember I said that 23, and I said when you Chebyshev rule, it's like, okay, that would be about 95% of all men. They'd be above. Well, actually, it's closer to 99.9% of all men that they'd be greater than. Okay. So why do we care?
Go back to the other slide.
I've got it. There you go. So the question is why do we care? Why is this important? Anybody know how tall that door is? Way greater than 6 feet.
6'9".
It's actually exactly 80 inches. Which would be 6'8". Okay, it's exactly 80 inches. That is the standard height for a door in the United States, is 80 inches. Why?
Because they got the average of like women's and probably the standard deviation of them.
Yeah. Obviously, the reason I'm asking has to have something to do with this, right? Basically, that's what they looked at. They looked at and now, don't take this as sexist at all. We don't need to actually think about women in terms of this because women's heights are typically, on average, smaller than men. So they look at male heights. And that would be higher. So the average male height is about 5'9", 69 inches. 3 standard deviations is just under 80 inches. So what that says is that approximately 1 out of 1,000 men would hit their head on that door. Okay? They're happy with that number. They're fine with that number. Because if I had to make it because every time I make things bigger, it costs more money. So they don't want to have it set for the average of 5'9", because that would cause at least half the men to hit their head. So that would be a problem. So, but when they go out to the 3 standard deviations, that becomes a very small problem. So it takes care of the vast majority of all those situations. Okay? So there was a situation, I believe it was in New York, a long time ago. There was a boat, a party boat. Anybody ever been on a boat? What's 2 of the things they always have on when they look at, not necessarily a little boat, but a traditional boat, they have 2 things. They have capacity, the number of people, and the weight. You also see this in elevators. You see the weight and you see the number of people. Okay? Well, the reason you see both now is because of situations like this. Typically, it was just capacity. They used average. They used standard deviation. They figured out that 12 people on average weigh 180 pounds each, so that the capacity of the boat would be this. We use boats because boats are buoyant. You put too much weight in it, the boat sinks. Okay, there's a specific value that boat can't be above before it actually sinks because it's not buoyant enough. Well, what happened was this boat was hired by a bachelor party. So they were all men. They were all a little overweight. The boat capsized. Because they didn't have more people on the boat than they were supposed to have. But the weight was a lot higher than the averages, because when they looked at the average for that, they looked at average for all people, which brought down that weight number. And when you only have, because typically you'd have a mix of people on the boat and it wouldn't be an issue. But when they were all a little overweight, all on the higher end, it caused a problem. That's why you start seeing the weight number now in the elevators and in the boats, because they actually have to worry about that. Planes do too. That's why you pay extra for larger bags and stuff like that, because it costs money for the actual airline. It costs them for gas and stuff like that to take that extra weight onto the plane. So we start looking at using this data to do pretty much everything around us is based on these averages that we use, and making sure that the stuff that we have is designed in a way that the vast majority of people would be able to be successful or survive it. Okay. Same thing with cars. Like the average, when they look at designing a car and a seat and how far the pedals are away and everything else, it's all designed around an average person. And then it moves to accommodate that change in standard deviation, but not to the point where it would have a extreme case in one way or the other. So if you're extremely short, you might need to do something extra to your car to make sure you can reach the gas pedals and stuff like that, because it's going to be further off than 3 standard deviations, which is what they base pretty much everything on. Does that make sense? All right. This is one class that you'll never sit there and go, why am I doing this? Because I could literally make a connection for this with everything. One math class, you'll never ask why. All right, so let's look at this one. So this is PCB concentrations in, I think these were egg, some kind of an egg. Hold on. Because I can't honestly remember the name of the egg. It was like pelican eggs, if I remember right.
And the Kappa pelican eggs.
Yeah, I thought they were pelican eggs. So these are basically pollutants in pelican eggs. So the mean, so first off, is this approximately a bell curve?
Yes.
Yeah, it's pretty close. A bell curve is going to have the majority of data in the middle, and then the sides are going to be mostly symmetrical. The more data we get, the more symmetrical it'll be, but it's pretty close. They found the mean is 206.45 parts per million, with a standard deviation of 66.42 parts per million. So if I was to pick a bunch of eggs, how many of those eggs would be within 1 standard deviation of the mean? Very good. I would expect to see 68% of the eggs within 1 standard deviation of the mean. Now, is that range? So find that piece.
Between 100.
1 standard deviation.
Mr. Baker, one
Yep.
more question.
Yep.
You want us to do that on our own, or just to tell you right now?
If you have the data because you found it, you can tell me. If you just looked in the book, then don't tell me.
Never mind.
Because one of the things I want you to be able to figure it out. Like, yes, I understand the answer in the book because I pulled the example from the book. And I'm going to copy and paste it from the book in a second. Because I'm not doing all the calculations out. So it's 1 standard deviation away. So we're going to add the 66.42 and subtract the 66.42. Yep. So 1 standard deviation is 140.03 to 272.87. So that's 68%. It's from there to there. Two standard deviations. So if I went from there to there, that's how much? Yes. 95%. So I went from 73.61 to 339.929 is 95%. And then 3 standard deviations. So if I went all the way across, that's the 99.7%. So the key to the empirical rule is 1 standard deviation 68, 2 standard deviations 95, and 3 standard deviations 99.7. Just on the picture. All right. So this one makes it a little more precise, but it's still 68, 95, 99.7. What is this? This graph shows it just broken down by hats, right? So we've got the left side and the right side. So if I'm over here, if I'm right here, that's where I am. How much is on this side of the graph? There's 0.1% left over, right? So right there is 99.9%. So if I'm right there, I'm higher than 99.9% of all people. If I'm 2 standard deviations away, if I'm right here, I'm actually at, was it 97.8%? So I'm at 97.8% if I'm at 2 standard deviations away. Above. So where's 95%? If I was in the 95th percentile, where would I be? All right. So somewhere between 1 and 2, right? Okay. So the empirical rule works really, really well for very specific numbers. 1 standard deviation, 2 standard deviations, 3 standard deviations. If I want anything other than that, I don't have a rule specifically for that. So I have to do a calculation. So what's standard deviation telling me? How far away from what I am? The mean. So we have something called a z-score. The z-score is taking whatever value I have and subtracting the mean and dividing it by the standard deviation. Okay? So this is basically telling me how many means I am away, or how many standard deviations I am away from the middle, from the mean. So this allows us to find any number. This is how your doctor would say you're in the 95th percentile or the 80th percentile or the 72nd percentile. Because they would take your weight, height, whatever, subtract it from the mean, and divide by how many standard deviations are. Okay. All right, so let's look at an example. let's get it away from people and talk about golf. So the Augusta National Golf Course, actually, I think they have more than 18 holes there, and I'm not sure how many holes they actually did with this one. But the mean length of a golf hole is 413.1 yards, and the standard deviation is 132 yards. So we want to find the z-score of Juniper's length, which is 180 yards. So remember I said the z-score was the value that we're looking at. So in this case, that's 180, minus the mean, which is 413.1, divided by the standard deviation, which is 132. So 180 minus 413.1 divided by 132. And you should get negative 1.765 or 66. All right. So what's that mean? What did we find? Okay. And what's z-score?
How far away you are from. Sorry, I wrote what you said.
That's fine.
But so it would be
How far we are away from the mean.
of the mean.
Okay. And it's not necessarily how far, it's how many standard deviations we are away from the mean. So the empirical rule gives me in whole numbers, 1, 2, and 3. The z-score will allow me to come up with specific values of that. So we are 1.766 standard deviations above or below the mean?
Below the mean.
Below, because it's negative. So negatives are fine in this. Negatives mean you're below the mean. Positives mean you're above the mean. If you're exactly at the mean, you would be at what? 0, because I'm right at the mean. So the mean would be 0. Okay. Now we want to somehow change that into a percent, right? Don't worry, this is the easy part. If you have your book, go to the back of the book. There's a Z table there. If you don't have your book, I'm going to put one on the board, but you can easily do a Google search for it. All right. So you should have a table that looks similar to this. It could be a Z table. That's T. That's T. Should be actually it's right at the back of the book. It's the very last pages of the book. No, literally the actual back of the book.
The cover.
It's the cover of the book. Yeah, it's literally the right back of the book. That's how important this is. They literally gave it the most important spot in the book. Okay? So, because we're going to use it a lot. So we had, what was it? Negative 1.76? Okay. So if we go, notice how there's the negative values. So we're going to go down to negative 1.7. And then we're going to go over to 0.6 or 0.06. So that is negative 1.76. So that means that right there, that's going to be my percentage. We've moved the decimal 2 places. So it's at 3.92%. It's bigger than 3.92% of all the golf holes at Augusta. Okay? So what the Z-score allows me to do, and you just notice tons of percentages here, it allows us to find the percentage of an exact value. Okay? Yes.
I think I'm looking at it wrong. Mine says 0.96. No,
That would be probably why. Yeah. You're welcome. Yeah.
Would you want this in percentages or just leave it at the decimal?
You can leave it as a decimal, actually. We're going to use the decimal more often than the percentages. We've just been talking about percentages, so I wanted to make the connection back to it. Yeah, but when we move into the other stuff, we're literally going to use them as this number. Yes.
How did you get 0.0485 or like whatever?
So
you were
negative
doing?
1.7,
Yes.
and we go over to 0.6.
Go over to 0.6.
0.0392.
0.0392.
Which is what?
Oh, I was looking at the wrong
I got
Z-score. My bad.
Yeah, that's right. It honestly, if you are going to use this a lot, a ruler really helps to make sure you go directly across, because it's really easy to go across and down by one or up by one. So rulers definitely help in this situation. All right. So I want you to find me 95%. So where would 95% be? Positive or negative side? Positive, because it's above 50%, right? Okay. So find me basically, so 95% would be what is a decimal? 0.95, right? So find me 0.95. Yeah, it's approximately 1.65. Yeah, 1.65, 1.64. It's actually specifically exactly 1.645. Specifically. But so that right there, that's 95%. So the 95th percentile isn't even at 2 standard deviations. It's at 1.65 standard deviations. Okay. So you can start to see how, like, when we're looking at like percentiles and stuff like that, you notice it gets really like big quickly. Like the majority of the percentages are very close to that junction point. So, all right, yes.
How would you pick which one?
What do you mean?
So how would you pick whether to put 1.64 or 1.65?
It just depends on what they're asking it around to. If you'll notice, I don't know if it's on yours. Some of them have a table for the very specific ones, like that we typically use. We use the 95, we use the 99 or 97. We use those percentages. So typically there's a number there for them. This one that I found doesn't have it. But I will give you those when we're going to actually start doing those calculations, those specific ones. I will give you the exact value that I would want you to use for those. All right. So find me the Z-score for, oh, sorry, let me go back. Switch screens. For the 495. So we're going to do the 495 minus 413.1 over the 132. What do we get?
Here.
All right. So that's between 1 and 2 standard deviations, right? Or no, 0 and 1 standard deviation. It's not even quite 1 standard deviation away. So if we looked at our Z table for that, so 0.62, you should get 0.7324 approximately. I think yours goes to 5 decimal places. But it's so that even though it's not even at 1 standard deviation, it's greater than 73% of all the other holes. Okay. All right. We are quickly running out of time, and I have the next thing I have to actually go over. All right. I spent way too much time on that, but that's fine. So we have a way to look at the exact specific percentile and stuff like that. But a lot of times we just want to know about what range we're in. We don't need to know the exact percentage of where we are. We want to know a range. And that's where quartiles come in. So if you remember when you got your SATs or ACTs and stuff like that, you probably got your decile. It's decile. It's actually the 10th instead of quartile. Quartile is just 25%. So we want to be able to split data into groups of 25%. And you probably have seen this before. This is a box and whisker plot. So the quartiles are the first quartile, second quartile, and third quartile. The quartiles are a specific number. So if you want to split something into 4 pieces, you actually make 3 cuts. And that's going to split it into exactly 4 pieces. The quartile is the cut point. It's the point between 2 pieces. Your second quartile is the median of all the information. Notice we're not talking about mean, we're talking about median. Why would we be talking about median in this case and not mean? What does median do that mean doesn't? Yes.
It is resistant to extreme observations.
Right. And it also cuts the data exactly in half. Half the data is on one side, half the data is on the other side. Okay? Because mean can be shifted by those extreme forces, so it might not be exactly in the middle, or median is always right in the middle. So the second quartile is the median of all of your data. The first quartile, once we split the data in half, we can split the first part in half and the end part in half. That's your first quartile and third quartile. Okay, does that make sense? Is that simple enough? You're basically going to cut your data into 4 pieces by cutting it 3 times. Median, median, median. We're going to do this, don't worry. We'll come back to interquartile ranges in a second. All right. On one line, it is very important to do this on one line. Write these numbers in order. Yes. That is exactly what we're going to do. Huh? You write the numbers in one line. We're going to put the box and whisker plot directly underneath it. There's your numbers in order. How many numbers do we have? 20. It actually said it in the problem. There's 20 numbers. All right. So how do I find the middle one? No, that's the median. I'm sorry, that's the median. We want the median. So we're going to count. So 20 numbers, the middle should be right around is 10, right? So if we count in, so you could, if you want, go this way. This way is some way people do it. So I have 2 numbers off to the middle. Okay, I'm going to undo those because I don't want the actual marks on the lines because I need them for other things. All right, so my median's right there. So my median's going to be what? Right, because if I have 2, I add them up and divide by 2. So my median, so my Q2 is 30.5. That's my Q2. So that now splits my data in half, correct? Okay. So I want to find my median of my lower half now. So we're going to do the exact same thing. But we're just going to look at the first 10 numbers. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I have 21 and 25. So again, add them up, divide by 2. So my Q1 is 23. Have I lost you yet?
I wasn't listening to the second part.
I just found the first, huh?
I was agreeing.
It's okay. I need to find the median of this lower half.
Okay.
So do the exact same thing. In this case, it's 21 and 25 are my middle 2 numbers. Add them up, divide by 2. And now we have to do it to the upper half. And we get 35 and 38, which is 73. So we got 36.5. So that's 36.5. All right, so I have my box. That's Q1, that's Q2, that's Q3. So that's my box. What would be my whiskers? Yes, my minimum and my maximum. So my minimum in this case is 5, and that's my min. And my maximum in this case is 66. But we're going to find out something interesting about 66 in a second. That's a box and whisker plot. We're going to make one change to it in a minute. What's my interquartile range? So my interquartile range is the difference between Q3 and Q1. So I'm going to take Q3 minus Q1. which in this case is going to be 13.5. So my interquartile range tells you how far it is from Q1 to Q3. Again, that gives me information about the spread. Okay, I know 50% of my data is between Q3 and Q1. So 50% of my data is there's 13.5% change in that. All right. The last thing we need to find is what's known as outliers. Why are outliers a problem? They can skew my data. So the outlier is a very specific meaning. Your outlier, not Q, out, O, is 1.5 of the IQR. So we take the interquartile range and multiply by 1.5. And the outlier is farther away from it than that. So what's 1.5 times my interquartile range? What was it? 21.5? Oh, 20.25. Okay. So to find an outlier, it's got to be farther away from Q1 or Q3 than 20.25. So if we were to subtract 20.25 from 23, I would get something less than 3, right? I think it was 2.75. Do I have any numbers lower than 2.75? No. So I have no outliers on the low side. I'm going to add 20.25 to 36.5, and I get 56.75. Do I have any numbers bigger than 56.75? Yes, that's 66. 66 is an outlier. So I do not need to actually claim that as my max. My max,
Wait, where did we get this from?
we added the 20.25 to my Q3.
Oh, right.
So my max is going to be 56.75. And then I put a star at 66 because that's an outlier. So the maximum is going to be where the highest that we could go is, which in this case is 56.75. Even though it's not one of my numbers, that's fine. And then I have an outlier at 66. All right, for those of you who love writing down notes, there's the actual definition of your outliers. That's the lower limit and the upper limit, which is going to give you, which if anything's outside of the lower limit or the upper limit, they'd be considered outliers. So an outlier is not just a specific number. It actually has very specific meaning in the calculations. And there can be multiple outliers. That is possible. And there's the exact procedure to how to create a box and whisker plot. You determine your quartiles, or determine any potential outliers. You're going to mark the, you're supposed to actually draw the lines, like the actual number line. You're going to mark your Q1, Q2, and Q3. Draw your box to make those. And then draw your lines out to your min and max, or the lower limit or the upper limit if there's outliers. And mark each outlier with an asterisk or a nice little star. So your 5-number summary is your min, your Q1, your Q2, your Q3, and your max. So it just gives you another way to look at data and give information. I spent a lot more time on the empirical rule and the z-scores and stuff like that because you're going to use that a lot more. But just like bar charts and histograms and pie charts, you see box and whisker plots. And that's information that you do need to know how to do. Yes.
How do you find the z-score?
That's the formula. The mean minus, it's the number you're looking for minus the mean
Number four
divided by the standard deviation.
minus the mean divided by the standard.
Yes. All right. Your the practice test will be posted probably in a half hour or so. As soon as I get the meet recording, so I can post everything up there today. So that'll be posted up there. If you have any questions on it, ask, and then we'll go over everything on Tuesday. And your test is on Thursday. Don't forget, I did say that you will be able to replace one of your tests with the final exam. The other thing, which I don't think I mentioned, is the opposite direction. Since I will replace the lowest test grade with your final exam, if you don't have a low test grade, I don't have to replace the final exam, so I'll replace the final exam. So if you have A's on all your tests, you do not have to take the final exam. So as long as you have an A in the class before the final exam, you're fine. All right, so if you do bad on a test, I'll take the final exam to replace it. If you do really well on all your tests, I use the test to replace the final exam, basically. Okay? So keep those things in mind. And you are allowed in the next card, 4x6 is fine, 3x5, whatever one you have. That is your cheat sheet. That is your cheat sheet. So you will have that. And have some way to, a nice little calculator. Make sure you have a calculator. And make sure you find a standard deviation calculator that you like to use online, because you will need those two things as well.
You can use our phone calculator.
Yes, you can use your phone calculator, yes. I would suggest, again, finding one that you can see everything you're typing in. So not like the standard calculator, you can't see what you're typing in a lot of times. So make sure you find one that you can see what you're typing in. This way you can check and make sure you didn't screw up a number. Okay? So, but yes, you're allowed to use your phone calculator. All right. Have a wonderful weekend. I will see you on Tuesday. I'll see you on Valentine's Day. You too. What's up?
Hey, so I have